Hello, my name is Richard Gasaris,
Hello, my name is Todd Troba.
I'm Eric Lee.
Hello, I'm Evan Saunders.
and we are
Crustacean.
Measuring 2 times the size of Texas, the Great Pacific Garbage Patch is a growing plastic island floating in the Pacific Ocean. Due to currents in the ocean, tons of plastic waste are building up the garbage patch every single day. It is now estimated there is 16 times more trash in the ocean than originally thought. One of the most pervasive components of the garbage patch are microplastics, which are damaging delicate ecosystems.
At Crustacean, no plastics will go to waste. With our system, we clean up the ocean trash gyre, save the marine ecosystem, and recycle the plastics for materials. We have a 3 main part system: a solar-powered water drone, a buoy with a magnetic ring and GPS signals. Attached to the buoy is a trash collecting bin that captures microplastics in the ocean, all autonomous in an efficient synchronous system. Crustacean aims to help stop the ever-worsening problem of microplastics in our oceans. These huge plastic gyres are out there in the ocean, and we can collect them and turn them into reusable materials. Our end goal is to make a cleaner ocean and turn the microplastics that are harming our ocean into reusable materials.
As Crustacean, we are ending the cycle of single-use plastics. The nature of our effort is conservation. We designed a system to collect microplastics with the intention of establishing a profitable businesses.
Here's our background and motivation. You gotta know your enemy, and the enemy is the Great Pacific Garbage Patch. This is a large area of marine debris trapped in the North Pacific Gyre, a large circulating current. The Eastern Garbage Patch specifically is located between Hawaii and California and has an estimated size of 1.6 million square kilometers, which is more than twice the size of Texas. In the gyre, the vast majority of the trash is microplastics, which is defined as less than 5 millimeters in size. Much of this comes from larger pieces of plastic breaking down but not decomposing due to sunlight and erosion in the seawater. It's estimated to contain 80,000 metric tons, which equates to 1.6 trillion individual pieces of trash, and it has a density estimated to range between 10 and 100 kilograms per square kilometer. Don't think of it as a big island that you can step on, though. The garbage patch is more like a milky soup. Microplastics can pose a big health hazard to ocean wildlife. Microplastics floating on the surface can limit sunlight to plankton and algae below, affecting the food web. In addition, fish and sea turtles eat microplastics, mistaking them for food. This just passes higher up the food chain to larger animals like tuna, whales, sharks, and eventually humans. Another issue is that microplastics can absorb toxic chemicals, which we don't want to end up inside of us or the wildlife we eat. Microplastics cleanup is a massively complex, multifaceted issue. So what's our solution to properly collecting and disposing of these microplastics? We'll talk about that next.
So we start off with the initial design with 5 requirements: low cost, marine friendly, autonomous, self-powered, and low maintenance design. Initial design we came up with are based on the floating sea beam trash collector already been made out there. We also implement the microplastic filter in our new sea beam. Now, let's talk about terminology. The sea beam works based on the up and down motion between the inner and outer bin. We believe that we can make improvement. We want to take out the pump component and rely on the wave movement to power our bin. Instead of using mechanical pump, we look for a different source of natural power such as compression spring force and magnetism in our component. The new spring and magnetic component will be placed between our inner and outer bin. With the water flowing in the inner bin, it will weigh down the spring and the magnet. Thus, the compression spring and repulsive magnetic force will push the inner bin up again, and then the process repeats. While this is happening, we have one-way valve at the bottom of the bin to get excess water outside of the bin, relying on the pressure from up and down motion of the whole mechanism.
As time has passed, we've advanced our design to this current concept. We now have a more realized locker design, which is meant to efficiently capture and hold onto microplastics while also keeping larger pieces of debris out with the use of raised guards. Here you will see that as water passes through the top, it will fall through our funnel and into the internal bin, which houses our net lining. The funnel is designed like this so that in the case of high seas, the locker won't lose its microplastic cargo. Here you will see a close-up of our lockers as well as an exploded view of all the parts that make it work. The magnets and spring you see have all been chosen to get the correct movement pattern for the water to properly escape through one-way valves placed on the holes of the outer bin. In order for the lockers to be effective, we will mount them onto special buoys that will be strategically placed in the Pacific and will drift with the currents through the ocean and the gyre. The buoys will have solar panels on them as well to power a transmitter that will relay information back to the mainland, such as its GPS position and whether a bin is full or detached. Next, we would like to introduce our autonomous solar-powered water drone named Davvy Jonez. Upon receiving a message from the buoy that a locker is full, Davvy Jonez will deploy with a fresh locker and bring it to the buoy utilizing the GPS signal and then return to the mainland with the full locker. Davvy Jonez will be mainly battery powered, and these batteries will be charged by solar panels on the top of Davvy Jonez. The journey that our drone will take is meant to be more passive so that it isn't invasive to marine life as well as other vessels in the ocean. While this is our final envisioning for Davvy Jonez, we plan on creating a prototype that is meant for more of a proof of concept.
Here we have a small simulation of the process when the drone come and pick up a full locker. Note that here we don't have the buoy attached the full locker around it, but we just focus on the simulation of the action of picking up the locker.
Our sea bin collector will consist of 9 parts. The estimated material cost will be $1,074. On the inside of our bin, we have a nylon 6 200 micron net. This net is recyclable, water insoluble, and will not contaminate the water or fish with any harmful chemicals. The reasoning for the 200 microns is that it will allow microplastics into the net while the major pieces of plastic get filtered out. The net will go inside of a metal bin that is made of nickel alloy 625. This metal is very durable, low maintenance, and saltwater resistant. On the outside of the bin we have a HDPE tube, which is made of high density polyethylene. HDPE is very durable, buoyant, resistant to seawater and UV rays, and has a longevity of about 50 to 100 years. Between our plastic bin and metal bin, we have magnets and springs. The springs will be chrome silicone alloy steel, which will be seawater resistant. The magnet will be a neodymium N42 rare earth magnet. The top of the bin will have a funnel with a check valve to allow bigger plastic trash to be filtered out. There will be a neoprene rubber sheet to cover between the two bins and keep water out. There will be U-bolts to connect the springs to the bottom of the bins. There will be a flotation device around the bin, which would be custom built to accommodate the locker. The valves will be placed on top of the funnel to filter out big trash and on the bottom to filter out water. We will be using check valves. Check valves are one-way valves. They can be manufactured by us, or we can use pre-built valves. The Davvy Jonez drone will be made of HDPE material and will have an engine, claw, solar panels, solar panel covers, and GPS system. The estimated cost of the drone is around $3,500 to $4,000, but is subject to change. The recycled plastics market is a growing market. As of 2020, the market is valued at $39.47 billion US, and it is estimated to reach $54 billion US by the year 2025. There is a great market for recyclable plastics. Companies such as Adidas make an estimated 40% of their clothing with recycled plastics. Nike also uses recycled plastics to make shoelaces and other components of their shoes. Recycled plastics can be used to make many items like reusable cups and tableware, packaging for food, building materials, backpacks, blankets, rugs, and rubber planters. We at Crustacean believe our design is feasible as our cost is relatively low, we have a self-sustaining system, and will be low maintenance. Compared to other solutions for plastic pollution, we have a system that requires little manpower to operate. Many of the other ocean cleanup solutions focus on the big pieces of plastic, but at Crustacean, we want to focus on the microplastics. Microplastics are recyclable ready, unlike large plastic that has to be broken down in order to use. We believe we have a quality solution to the growing problem of microplastic pollution in our oceans.